guys, I'm William, the competition leader for the math club at La Quinta High School. I'm a current senior heading into my third year with the club. A fun fact about me is that I actually studied math in fourth grade, in which I gained more knowledge in math so quickly to the point that I mastered a lot of subjects in mathematics. Anyways, this is the guide to math competitions. I'll be explaining what they are, talking about their difficulty level, giving you guys some tips, and going over some of my personal solutions to these problems. I'll be doing this at the high school level because I feel like it's not only nearly impossible to solve problems from the last Olympiad for most of us, but I feel like the strategies may be helpful in general. With all of this being said, let's dive deeper. What are math competitions? These are competitions in which you have to solve a number of math questions with a certain time limit. These problems are really hard. How hard? For example, when the contests were offered at my high school, they were so far from the normal test questions in my school system's curriculum. It seems that you need to know geometry that's slightly more advanced, number theory that most math teachers never teach, or a subject that most competitors just don't understand. There are competitions that may require you to work with other teammates, but they're mostly individual performances. I say they're a great way for you to challenge yourself. How well do you know math? If you're already excellent, you just keep going and you get much, much better. But if not so much, don't worry. These competitions may serve as great tools for you to improve and become much better at problem solving. I'd say, if you're bored, you should definitely try one of these. There's so many examples of math competitions. Worldwide, we have the IMO, International Math Olympiad, RMO, Regional Math Olympiad, USAMO, USA Math Olympiad, Putnam Exam. These competitions are all prestigious and that it is extremely difficult to get the questions correct. But at the high school level, there's the CAML, or I can say CAML. It stands for the California Math League, AMC, American Math Competition, AIME, American Invitational Math Exam, Purple Comet. These questions are substantially easier, as it may be easy for the best Olympiad contestants, but as you see in my school, friends of mine struggle to solve these questions. It's going to serve as a testament to the challenging characteristic I discussed earlier. I said that these competition questions were hard, but how hard? Really? Was I lying to you? I invite you to solve this problem here. Can you figure it out? Pause the video and try to come up with all the solutions before I reveal. Ready? Here are all the solutions below. At this point, I know what you guys may be thinking. These competitions are daunting, not worthwhile. We're cheated here. But it's not all that terrifying. There are many ways to approach every problem in the competitions, and I'll go over several methods right now. First, start small and find patterns. Whenever you have a problem that's dealing with a large number of objects and you can't easily determine the structure of the solution, it's maybe a great way to start with smaller cases. Once you have solved the problem with many of these small cases, you might see a pattern emerging. If you have enough time, I recommend you try to prove the pattern. Either you use deductions or math induction. What's induction? Use a base case, smallest case, prove that if one case works, then the subsequent one works as well. In other terms, you prove statement 1 works, the truth of the previous statement means the truth of the next statement as well. Second, there's casework. I don't like this method as it's too long, but it may be the only way to arrive at the solution to a certain problem. For example, if you research the four-color theorem, you see that the only way to prove it is to use casework. So what is casework? It's a method that you split a problem into several cases, then you analyze each separate case. For example, to prove statement A is true for both conditions 1 and 2, you have to prove for both condition 1 and 2 separately. When it's appropriate to divide the problem into many subcategories and work with each subdivision, like whether the number is odd or even, I recommend you use casework. Work backwards. Sometimes a logic problem requires you to solve the step backwards so that you can trace back the steps more effectively than if you went forward. For geometry problems, I call it adding lines. It's a versatile strategy as you can more easily visualize and solve the problem. For example, you can create triangles that allow you to solve for certain side lengths and angles that may allow you to solve the bigger questions. Connect and translate the problem. It's like bijection. Can you find a problem similar to the problem you originally have, but it's much easier to handle, and it's exactly a bijection? For example, the Gaussian sum, 1 plus 2 plus da 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 plus n, you don't have to solve it the way Gauss did, but we can translate into an area problem by imagining each as a tower of squares or blocks, and then we realize it's an area problem that has one big triangle plus n small triangles, and once we find the area, we get the famous sum. I have this method here because for some problems, you may have to experiment and combine the conditions and or deductions to get the solution. I'm talking about this method for some problems in which the conditions don't mean anything at first, but when you use them together, you get major deductions that could be enough to obtain the solution. For example, you may have two equations, Diophantine equations, and you have to prove that x and y have certain parities or equal to some modulo, equal to something modulo 3, for example. If you have an equation like this, if you have two equations, it might not mean much, but when you combine them and then you use certain tricks to reduce the equations into something, that's when you can prove the result. I'll explain some tricks in the next slide, but in general, you have to carefully analyze the problem and see what approach works for it. Look up solution guides and previous competitions to practice and learn so you can be more prepared for future competitions. What tricks are there? There are a plethora of tricks to use. Like, you can research algebraic identities. There's the Fermat's little theorem for number theory, Simon's favorite factoring trick with Diophantine equations. Symmetry, that's one of the most invaluable ideas. And to cap all things off, geometry theorems and lemmas if you're stuck with a hard geometry problem. These are just examples, but make sure that if you can, use them. How do I solve problems? First, I read the problem carefully, look for the best approach, think about what I already know that helps me solve the problem, like prior knowledge that helps, and then the last step, to put everything together. How about we go through 5 examples and we'll see how we do. Number 1. This was the first problem of the 2023 Camel contest in February. If x over x plus 2 is 2022/2023, what's the value of x plus 1 over x plus 2? For algebra kids, this is going to be easy. You can just solve for x and you plug x into the required expression. You should get 4045 over 4046. This is problem 3 of the November 2022 Camel contest. Of the 100 fractions whose numerators are integers from 1 to 10 and whose denominators are also integers from 1 to 10, what percentage are already in lowest terms? It seems like we have to use casework. So what are lowest terms? That means the fraction is already reduced because the numerator and denominator have no factors besides 1. The nature of whether two numbers have a common factor other than 1 is not really predictable, so casework is most effective. Do we have a trick to save time? I'd say the best way is we set the numerator to 1, then we check each denominator possible, then we have to check the numerator equal to 2, then check each denominator, and you keep going until you get to the numerator equaling 10, and then you finish checking all the denominators, in which you can arrive at 63% of the 100 fractions that satisfy the conditions of the problem. Number 3. It can be proven that the trinomial 4 raised to the 2000 power plus 4 to the x power plus 4 to the 2023rd power is the square of an integer for exactly 3 values of x. What's the largest such value? This is the final problem of the March Camel contest of the 2023 term, yet this is going to be argued as the hardest problem of the term. For me, to explain the solution of the problem, the easiest way is, can I relate this problem? I mean, there are 3 atoms in the sum, I know a squaring formula that also has 3 addends on the right hand side. Below is the formula that everyone from algebra should be familiar with. A plus b squared is equal to a squared plus 2ab plus b squared. Now we can equate the two expressions, addend by addend, and solve the corresponding system of equations. For example, if a squared was 4 to the 2000th power, 2ab was 4 to the x, and b squared was equal to 4 to the 2023 power, then we can solve for the values of a and b, then plug that into the 2ab equation, solve for x. But we have to be a bit careful. Just note that in addition, we can rearrange the addends in each expression to get a different order of addends. For example, I can switch the first and second terms and we get a different system of equations. So be mindful of the permutations and make sure you do not leave out any possible solutions. Once we cared for all the permutations, we get that x is 2045. Number 4. I put 2 problems on the February Camel contest because of how related they are. We got problem 3, for what value of a will a circle of area a quadruple its area by increasing the length of the circle's radius by 1. And problem 4, the sum of 3 consecutive terms of a geometric sequence is 62. If the sum of the common logarithms, the base 10 logarithms of these 3 terms is 3, what's the value of the greatest of these 3 terms? When we set up these problems, we see that we have to crack the system of equations for both instances. For the first system, I would use substitution, set the a expressions equal to each other, and solve for r. For the second, clear fractions in the third equation, clear logs in the second equation, and realize that I can substitute xz for y squared in the second equation. Then I would get y equals 10, xz equals 100, x plus z equals 52 by using the first equation, and solve for x to get x equals 52 minus z, plug that into the xz equation, and we get a quadratic at x, which we can solve if you know what the quadratic formula is. Eventually, solutions are pi for 3, 50 for 4. Number 5. This is the final example, but this is from the 2022 AMC 12 contest. To show for it is problem 5. The question, the taxi cab distance between points x1, y1 and x2, y2 and a coordinate plane is given by x1 minus x2. That's an absolute value, plus the absolute value of the difference of y1 and y2. So basically, it's a number of steps. It's in the compass directions to get to certain points. But for how many points P with integer coordinates is the taxi cab distance between P and the origin less than or equal to 20? That's the question. Let's assume we don't know how to solve with 20, so we just reduce the problem, change the 20 to 1. When we start with a small case, there's a pattern that I can see where the points form a diamond shape. When we count the number of points, that's 5. Then we solve the same question, but instead of 1 point or 20 points, we have 2 points. So we just keep incrementing the number from 20 we replace. That was 1. We increase by 1 until we notice a pattern. We get a diamond shape of points again. This time, the count's 13. Then I start to believe that the points form a diamond shape, but what's that number? There are so many ways to solve this problem, but what I would do is to rotate the diamond 45 degrees and see that there are 2 squares to count, and then the pattern becomes very clear at this point. Once you find the pattern, for example, the problem, when you replace 20 with n, the correct formula is going to be n squared plus the expression n plus 1 squared, and when you plug n equals 20, you get 841. That was the correct solution to the problem. And that's the end of the video. I really hope that I helped you guys understand what math competitions are and how to perform well or better in them. Thanks for listening, and I'll see you next time.